This paper is called Tackling the Awkward Squad for Reactive Programming, the Actor-Reactor Model. My name is Van Vonder, and there are two things that I want to convey in this presentation. First, what is the awkward squad for reactive programming? And second, what is the Actor-Reactor model? But first, I will give you some context. My work is in the field of reactive programming, which is a technique to write programs that are continuously reacting to incoming data. There are many incarnations of reactive languages and libraries in academia and in industry, and some of them I have listed here. And in the rest of this presentation, I will abstract over their details and I will talk about them in terms of their directed acyclic graph, or DAG. Consider this reactive program that converts Celsius temperatures to Fahrenheit. Its corresponding DAG representation shows how the data flows through the application. And in general, we say that the source nodes correspond to the input signals of the program, the internal nodes are operations performed on these signals, and the sink nodes correspond to the output of the reactive program. The ideas in this paper come from the observation that existing reactive programming languages and frameworks only focus on the internal part of reactive programs. So, they focus on the various ways and mechanisms to program DAGs. But reactive programs also have two other parts, namely an input and an output part. The input part, for example a thermometer, provides input to the reactive program by modifying its source nodes. On the other hand, the output of the reactive program may be used to modify a user interface. And we observe that reactive programming is only used to implement the internal part of a reactive program, and that it is usually embedded in an application that is still written in an ordinary imperative language such as JavaScript or Scala. And we have analyzed the problems that may occur when combining imperative and reactive code within the same application. Concretely, we have identified three concerns that we call the awkward squad for reactive programming. And they are related to long-lasting computations, to the embedding of imperative code within reactive code, and vice versa, to the embedding of reactive code within imperative code. After explaining those, I will explain our solution to this problem, which is called the Actor-Reactor model. The first concern is related to long-lasting computations or responsiveness. So responsiveness is one of the four key properties of reactive systems outlined in the so-called Reactive Manifesto, which says that responsive systems focus on providing rapid and consistent response times, establishing reliable upper bounds so they deliver a consistent quality of service. And we found that reactive languages and frameworks often impose little to no restrictions on the types of expressions that can be used within a reactive program. It is often easy to write code that accidentally makes the program no longer reactive. For example, consider this program snippet written in RE Scala, which defines a reactive value called matches that matches some user input against a regular expression. This regular expression matches all strings that contain at least one A at the start and a B at the end. The inexperienced programmer who wrote this expression is unlucky, since the worst case complexity of this program is actually exponential, and matching a string with 50 A's takes a huge number of steps before the match fails. We call this the reactive thread hijacking problem, because for certain types of input, this computation may take a very long time to complete. It can completely hijack the thread of execution, thereby stopping the reactive program from being able to react to any new input. The language design problem that needs to be solved is how to ensure that a reliable upper bound can be imposed on long-lasting computations within reactive programs, and we propose three levels of reactivity that provide different program termination guarantees. And while in this presentation I will not go into the details of how to enforce them, essentially, weakly reactive means that the language offers no guarantees whatsoever, eventually reactive means that the program will eventually terminate, and strongly reactive means that the program reacts in big O of 1. The second concern is related to the embedding of imperative code within reactive code, which leads to a problem that we call the reactive update order leak. So it is often easy to construct reactive programs where the internal update order changes the program semantics, which can cause extremely subtle and tricky bugs. For example, this program contains two print statements to print A or B, plus the value of some reactive counter to the console. And we found that the order of the print statements is switched in about 50% of executions. Most importantly, this non-deterministic update order is a correct implementation of the reactive language, and instead it is wrong for the application to rely on a specific update order. Finally, a third concern we identified relates to the complementary need to embed reactive code within a larger imperative program. A complete solution must be able to bridge what we call the reactive imperative impedance mismatch, so to bridge the gap from imperative code to reactive code and vice versa. In related work, we were able to identify a handful of partial solutions to this problem, which have limited applicability or unclear semantics. So clearly, there are some issues when combining imperative and reactive code. Our solution is to embrace that reactive applications always consist of both imperative and reactive parts, but we will keep those parts separated. And actors will be responsible for all imperative input-output parts of reactive programs, including all long-lasting computations. Reactors will encapsulate a typical reactive program represented by a DAG, and their operations must always terminate and cannot have side effects. And actors and reactors together interact via data streams which they produce and consume. So we built a language that we call Stella that implements the Actor-Reactor model. The reactive thread hijacking problem and the reactive update order leak are tackled via its object-oriented base language, and the reactive imperative impedance mismatch is tackled via actors and reactors. First, its base language. Stella is a dynamically typed class-based language where all runtime values are objects, and their classes are shared between actors and reactors. For example, here is the definition of a class pair that can be used to implement linked lists. It has two local fields called car and cooter, and a constructor called initializeWith that takes two formal arguments, initial car and initial cooter. Its body initializes the corresponding fields. Two methods on lines 11 and 12 are called setFirst and setSecond, and in their body they have an assignment to the car and cooter field. The big difference between classes in a regular OO language and in Stella are so-called routines. For example, on lines 8 and 9, two routines are defined called first and second, which return the car and cooter field respectively. Routines are special kinds of methods which have three crucial properties. First, routines have no side effects. A setBang statement in their body would be rejected by the compiler. Second, routines always terminate. We made Stella fall into the category of eventually reactive languages, which we can enforce via size change termination. Lastly, to ensure that these properties are upheld, routines can only invoke other routines. Stella will ensure that reactive programs in the form of reactors can only invoke routines on objects, which means that they are guaranteed to be free of side effects and that they will eventually terminate. Now I will solve the issue of coordinating imperative and reactive code using actors and reactors. I will show how actors and reactors work by implementing a simple wind turbine simulator that consists of three parts, namely the wind, which is continuously blowing, a wind turbine reacts to this wind and calculates its power output, and the console continuously monitors the power output of the turbine. There are three things that I want to show. From left to right, the wind will show how actors are used to create data streams, and it is implemented by an actor because its simulation is an infinite loop. Turbines show how data streams are processed via a functional reactive program. Then finally, the console is represented by an actor and shows how actors can monitor data streams. Stella actors were inspired by the ActiveObjects actor model, and the definition of their behavior looks similar to that of a class. For example, the code here defines a wind actor behavior that will continuously generate a random number to simulate wind speed. It has a local field called RNG and a constructor called init that will initialize the field. An atypical feature of our actors is the devstream declaration on line 2, which says that an actor that is spawned from this behavior will export a stream called speed with an arity of 1. While in this presentation I will not go into the details of stream arity, it essentially denotes the number of values that are pushed to the stream in one operation, and in the paper we use it for actor and reactor composition. Finally, the blow method on line 8 shows how values are pushed to the stream. Responsible for this is the emit statement on line 9, which will emit a value between 0 and 30 to the speed stream. After this, the actor sleeps for 10 seconds and then sends itself a recursive blow message to emit the next value. So how do we process a data stream? Traditionally, reactive programs consist of two layers, namely a single DAG and a reactive engine to propagate values. In Stella, reactive programs are described in three layers. A DAG is described by what we call a reactor behavior, of which there can be many. Because reactor behaviors can be reused and composed, we call one particular instance of a DAG a deployment of the behavior. Lastly, a reactor is a process which has a mailbox and a reactive engine that contains these deployments. For example, a wind turbine is represented by a reactor behavior called Turbine that implements the formula below. It calculates the power output using the three input arguments called blade length, which is expected to be a number, efficiency, also a number, and the wind, which is a reference to a wind actor from a few slides ago. It has two local variable definitions called swept area and wind power that together implement the formula at the bottom via regular invocations of routines, such as multiplication and exponentiate. And the reactor behavior has one output denoted by out, which is the result of the multiplication. This reactor behavior is compiled to a DAG just like a traditional reactive program. You can recognize the three inputs at the top, which are source nodes. At the bottom there is one sink node, and most of the nodes in between are applications of routines. Something that I wish to highlight is the compilation of a dependency to a data stream. In the body there is an expression theWin.speed, and this is what we call a qualification. In this case, it is a reference to a data stream called speed, exported by the actor stored in variable theWind. We compile this into two distinct nodes of the DAG, because there are two sources of change. First, the yellow node on the left manages the dependency to the correct speed stream whenever the reference to the actor changes, and second, the yellow node on the right receives the data that is continuously emitted to the stream. The final thing that I want to show you is how actors can monitor data streams for changes. This code describes an actor behavior called main with a constructor called start that on line 3 spawns an instance of the wind actor, and a reference to this new actor is stored in variable Mistral. Then on line 4 a blow message is sent to this new actor, and whenever the message is processed, the Mistral actor will start emitting new values. Then on line 6, an instance is spawned of the Turbine reactor behavior. A reference to this reactor is stored in Turbine, and at this point it is not reacting to anything yet. On line 7, via the react2 statement, the Turbine is instructed to change its source nodes to three values, namely 80, 0.3 and Mistral. So 80 meters blade length, 0.3 efficiency, and reacting to the Mistral wind. Using the monitor statement on line 9, the main actor that is being defined will monitor the output of the turbine. Whenever a new value is emitted to the turbine.out stream, this value will arrive in the mailbox of the actor, and it will invoke the corresponding print method defined on lines 11 and 12. So, to conclude, reactive applications need both imperative and reactive code. But when they are combined without constraint, they can lead to the issues of the awkward squad that we discussed. The main message that I want you to take away is that I think that they should be separated. Our proposal is to separate them into actors and reactors, where the imperative code runs in actors and the reactive code runs in reactors. The reactive code is both constrained in side effects and in termination. Both actors and reactors interact via data streams. And the combination of all of this can ensure that actors and reactors can essentially, remain socially distanced. And there are a number of interesting things that I wasn't able to talk about, for example, the composition and reuse of reactor behaviors, but for this, I can only encourage you to check out the paper itself. Thank you.